Welcome to our deep dive into Apache Kafka, a powerful distributed streaming platform that revolutionizes how organizations handle real-time data. As a central hub in the data ecosystem, Kafka enables seamless communication between producers and consumers, making it an essential tool for modern data-driven architectures. In this video, we'll explore key concepts of Kafka using a real-world use case and best practices for leveraging its full potential. To truly grasp the power of Kafka, let's consider a practical scenario where it plays a crucial role. Imagine a taxi service application that needs to efficiently manage and process real-time data from drivers and passengers. When a passenger requests a taxi, the system must quickly find the closest available driver, which requires continuously collecting and processing GPS location updates from all taxis. In this context, Kafka acts as the backbone, ensuring that every location update from a driver and every ride request from a passenger is handled with precision and speed. This real-time data is crucial for ensuring that passengers are matched with the closest available driver as quickly as possible. In our modern taxi service, built using a microservices architecture, we have two key services: the driver service and the ride matching service. Each driver's app is connected to the driver's service, allowing it to frequently send current location data to the system. The ride matching service, on the other hand, processes this real-time GPS data to find the best match for passenger ride requests, ensuring efficient and accurate ride assignments. To efficiently manage the flow of driver location data from the driver service to the ride matching service, we utilize Kafka. In Kafka, a topic is a dedicated stream of data, acting as a channel where related information is collected and stored temporarily. For our use case, we create a topic named driver location, which will hold all location updates sent from the driver service. The driver service is responsible for sending these updates, making it a producer in Kafka. It continuously publishes the latest driver locations to the driver location topic. Meanwhile, the ride matching service, which needs to process this data in real time to ensure accurate ride assignments, subscribes to the driver location topic and consumes the incoming data. This ensures that the driver locations are always current and ready for quick and efficient ride matching, positioning the ride matching service as a Kafka consumer. Here's how it all comes together. The driver service, functioning as a producer, sends each driver's location update to the driver location topic. This topic then becomes a stream of real-time location data that can be consumed by other services. The ride matching service, acting as a consumer, reads from this topic to determine which driver is best suited to pick up a passenger, ensuring efficient and timely matches. In Kafka, topics are split into partitions. Each partition is an ordered sequence of messages where the order is preserved. When data is sent to a topic, it's distributed across these partitions. By default, messages are assigned to partitions randomly, ensuring an even load distribution. However, when a key is provided for a message, Kafka guarantees that all messages with the same key are consistently sent to the same partition. This is achieved through a process known as hashing, where Kafka uses the key to determine the appropriate partition for each message. This mechanism is especially powerful when you need to preserve the order of messages for a specific entity or field, like a driver ID in a taxi service. For instance, if each message corresponds to updates from a particular driver, Kafka ensures that all updates from the same driver will always go to the same partition. This not only maintains the correct message sequence for that driver, but also makes it easier to process related data together in the same place. Whether you're tracking driver locations or processing trip completions, this key-based partitioning helps ensure smooth, organized data flows. Every message within a partition receives a unique, incremental ID called an offset. This offset is essential for keeping track of which messages have been processed, but it's only meaningful within its specific partition. It's important to note that Kafka topics are immutable. Once data is written, it cannot be changed. This immutability ensures data integrity. However, data within a topic is only retained for a limited time, which is configurable based on the needs of the system. Multiple consumers in an application read data as a group. When we use Kafka to scale our application, we often deploy multiple consumers within a group to efficiently process data. This is known as a consumer group. Each consumer within a group reads data from an exclusive partition of the topic. That means each partition of a topic is read by only one consumer within the group at any given time, ensuring that data processing is distributed and efficient. For instance, if our driver location data is split across several partitions, each consumer within the ride matching service will handle a unique partition, avoiding overlap and ensuring efficient processing. Let's say the driver location topic is divided into four partitions and the ride matching service has three consumers. Consumer 1 might read from partitions 0 and 1. Consumer 2 reads from partition 2, and Consumer 3 reads from partition 3. This setup avoids overlap and ensures that all partitions are covered efficiently. If the number of consumers in the group exceeds the number of partitions, the extra consumers remain inactive, acting as standbys. For instance, with 5 consumers in the ride matching service and only 4 partitions, consumers 1 to 4 will read from partitions 0 to 3, while consumer 5 stays inactive until needed. Kafka also allows multiple consumer groups to consume the same topic. This is useful when different services need to perform distinct tasks with the same data. For example, while one group of consumers processes the data for ride matching, another consumer group can consume the same data for analyzing traffic patterns, and a third group could consume it for monitoring driver behavior, all from the same stream of location updates. In our taxi service, let's say the ride matching service has 3 consumers, the traffic analysis service has 2, and the driver monitoring service has 1. Each group consumes data from the driver location topic independently, ensuring that all necessary processing tasks are handled simultaneously without interference. To manage these groups, Kafka uses the group ID property to differentiate between them. Kafka tracks the offsets, the specific points up to which each consumer group has read, ensuring that each group can pick up where it left off, even after a failure. When a consumer in a group processes data, it should periodically commit its offset. If a consumer fails, Kafka allows a new consumer to resume processing from the last committed offset, ensuring the data processing pipeline remains intact and resilient. A broker in Kafka is a server that receives, stores, and serves data, acting as the backbone of Kafka's architecture. A Kafka cluster is a collection of brokers. Each broker is identified by a unique ID within the cluster. In our taxi service, imagine we have a Kafka cluster composed of 3 brokers: Broker 1, Broker 2, and Broker 3. Each broker is responsible for holding specific partitions of the topics within the system. For instance, we can have a driver location topic with 3 partitions and a ride request topic with 2 partitions, both distributed across these 3 brokers. When a client, such as the driver location producer or the ride matching consumer, connects to any broker in the cluster, known as a bootstrap broker, it automatically gains access to the entire cluster. This is because every broker knows about all topics, partitions, and brokers within the cluster. This is known as broker discovery. Every Kafka broker acts as a bootstrap server. This means that you only need to connect to one broker, and your Kafka client will automatically know how to interact with the entire cluster. Each broker holds metadata about all other brokers, topics, and partitions. To ensure high availability and fault tolerance, Kafka supports topic replication. In a Kafka cluster, topics typically have a replication factor greater than 1. This means that each partition of a topic is duplicated across multiple brokers. For our taxi service, consider the driver location topic with a replication factor of 2. In this setup, if broker 1 holds partition 0, broker 2 might hold a replica of partition 0 and partition 1, and broker 3 could hold a replica of partition 1. This ensures that if broker 2 fails, the data is still available on broker 1 and broker 2. If a topic has a replication factor of 3, the system can tolerate the loss of up to 2 brokers without losing any data. So, with a replication factor of n, you can permanently lose up to -1 brokers and still recover your data. In Kafka, every partition has a leader broker, and at any given time, only one broker can be the leader for a particular partition. Producers, like the driver service, send data only to the broker that is the leader of the relevant partition. Other brokers that hold replicas of that partition will then replicate the data from the leader. For instance, if broker 2 is the leader for partition 0 of driver location, all updates from drivers assigned to this partition will be sent to the broker 2. Broker 1 will then replicate this data to ensure fault tolerance. These are known as in-sync replicas. In the Kafka ecosystem, Zookeeper plays a crucial role in maintaining high reliability and coordination across the cluster. It operates with an odd number of servers, ensuring stability and consistency by designating one server as the leader, responsible for handling all write operations, while the remaining servers act as followers, handling read operations. Zookeeper is also central to broker management within Kafka, maintaining an up-to-date list of brokers and overseeing the critical process of leader election for partitions. This ensures that data is consistently and efficiently managed across the cluster. Furthermore, Zookeeper continuously monitors the cluster, sending notifications to Kafka whenever changes occur, such as the creation of new topics or when a broker fails. This proactive monitoring helps maintain the overall health and performance of the Kafka cluster. Craft streamlines Kafka's architecture by eliminating the need for Zookeeper, making the overall system simpler and more efficient to manage. This evolution brings several significant benefits to Kafka, including improved stability and scalability, allowing it to handle larger workloads more efficiently. It also introduces a single security model, simplifying security management across the cluster. Craft ensures high availability by quickly electing a new leader after failures, minimizing downtime. Furthermore, its distributed controller architecture enhances fault tolerance and reliability, ensuring a robust and dependable system. In our taxi service use case, data is at the heart of delivering seamless experiences, from ensuring drivers are matched efficiently to optimizing routes for faster and more reliable rides. Kafka provides powerful tools like Kafka Streams, KSQL, and Kafka Connect that enable us to process, analyze, and integrate this data in real time. Kafka Streams is a lightweight Java library designed for building real-time analytics and event-driven applications within our microservices, allowing us to process data streams in real time. Kafka Streams enables powerful transformations, aggregations, filtering, and enrichment of data as it flows through Kafka. Developers can easily integrate Kafka Streams into their Java or Scala applications using the Kafka Streams API, which interacts directly with the Kafka cluster. For example, in our use case, as rides are completed, Kafka Streams can immediately process ride data to update overall driver statistics, such as the total number of rides completed, average trip time. Also, this library is not only elastic and highly scalable, but also fault-tolerant, ensuring that our streaming applications can handle fluctuations in load and recover from failures seamlessly. Kafka Streams supports both stateless and stateful processing, as well as windowing operations for time-based analytics. KSQL is a powerful tool that simplifies real-time filtering, joining, aggregating, and transforming data within Kafka topics using familiar SQL syntax. This allows us to perform complex analytics directly within the Kafka ecosystem without needing specialized coding skills. KSQL supports a wide range of stream processing operations, including aggregations, joins, windowing, and more, enabling distributed, scalable, and reliable real-time data processing. In the context of our taxi service, KSQL allows us to perform real-time monitoring and analytics. For example, in our taxi service, we can use KSQL to join two Kafka topics, trip data and driver info, to generate valuable insights. This process not only provides continuous, up-to-date analytics, but also integrates seamlessly with our existing Kafka infrastructure, allowing us to keep track of critical metrics as they happen. Kafka Connect is an essential tool for integrating Kafka with a wide range of external systems, such as databases, key value stores, search indexes, and more. It simplifies the process of streaming data into and out of Kafka, enabling seamless data flow between Kafka topics and other systems. With Kafka Connect, you can easily ingest data from external sources into Kafka topics or export data from Kafka to external systems. The Connect API provides a framework for building custom connectors that can continuously pull data from source systems into Kafka or push data from Kafka to target systems. However, many users won't need to interact with this API directly, as Kafka Connect offers a variety of pre-built connectors, allowing you to set up data pipelines without writing any code. For example, in our taxi service, say driver profiles are stored in a MySQL database that holds structured data. However, as we scale, we require real-time synchronization with a MongoDB database for more dynamic data, such as ride history and live updates. Kafka Connect bridges these systems, ensuring that any changes in MySQL, like new drivers or profile updates, are immediately reflected in MongoDB. This setup not only keeps our databases in sync, but also enhances our ability to run complex queries and perform real-time analytics. In any distributed system, managing data formats consistently is vital. Kafka's schema registry plays a crucial role by storing and managing schemas for topic message data, ensuring seamless serialization and deserialization across the network. It enforces strict schema validation, making sure that both producers and consumers adhere to the defined schemas, preventing errors and maintaining data integrity across the entire ecosystem. Schema Registry supports popular serialization formats like Avro, JSON Schema, and Protobuf right out of the box, and it enables schema evolution by maintaining backward and forward compatibility, allowing schemas to change over time without breaking existing data flows. Schema Registry provides a safeguard against data corruption by enforcing strict schema adherence. Also, it ensures that all data processing and integrations, whether through Kafka Streams, KSQL, or Kafka Connect, are schema compliant, enhancing overall data integrity across the system. As with any powerful technology, effective use of Kafka requires careful planning and understanding of its key principles. Let's review some common mistakes that can lead to suboptimal performance, data loss, and unnecessary complexity. Partitioning strategy and key selection are fundamental to ensuring that critical data is prioritized and processed efficiently. Misaligned strategies can lead to unbalanced partitions and uneven load distribution, which can severely impact performance. Incorrect handling of data serialization and deserialization, particularly without using a schema registry, can result in data corruption or compatibility issues. Ensuring proper serialization with tools like Avro, JSON Schema, or Protobuf is critical for maintaining data integrity. Although Kafka is excellent for replaying historical data and ensuring ordered processing, it's not meant to replace databases for complex queries or analytics. For these purposes, a relational database like Oracle or a NoSQL database like MongoDB would be more suitable. Inadequate broker configurations, such as improper memory allocation, disk setup, or network settings, can hinder Kafka's performance and scalability. Fine-tuning these configurations is essential for optimizing throughput and ensuring stability. Failing to monitor Kafka's performance metrics can lead to undetected bottlenecks, delayed identification of potential failures, and an inability to address performance issues proactively. Effective monitoring is key to maintaining a healthy Kafka cluster. Neglecting data replication strategies can lead to data loss during broker failures. It's crucial to configure replication factors appropriately to ensure data durability and availability. Without proper scalability planning, your Kafka infrastructure may struggle under increased load, leading to performance degradation. Planning for future growth is essential to keep your system resilient and responsive. Always design your Kafka architecture with scalability in mind. Use partitioning and replication strategically to balance load and ensure high availability. Incorporate a schema registry to manage and evolve your data schemas, ensuring backward and forward compatibility while maintaining data integrity. Regularly monitor Kafka's performance metrics like broker health, partition distribution, and consumer lag, and optimize configurations as your system scales. Throughout this video, we've explored the core components and advanced features of Kafka, using our taxi service as a real-world example. From understanding the basic concepts of producers, topics, and consumers to the importance of broker management and Zookeeper's role, we've seen how Kafka ensures reliable, scalable, and fault-tolerant data streaming. We also delved into the evolution of Kafka's architecture with Craft, the powerful data processing capabilities of Kafka Streams, KSQL, and Connect, and how the schema registry safeguards data consistency and integrity. Kafka is a powerful tool for building resilient and scalable data pipelines. By understanding its components, avoiding common pitfalls, and following best practices, you can ensure that your Kafka-based applications are robust, efficient, and future-proof. Thank you for watching and being part of this journey into object-oriented programming. If you found this video helpful, please give it a like and consider subscribing for more content like this. Don't forget to hit the bell icon so you never miss an update. Keep coding, and we'll see you in the next video.